Welcome back. We are going to continue our study of the spacetime algebra using our favorite paper here. And today we are now going to make a small diversion because we are approaching a very important topic, the topic of relative frames and paravectors. And this whole topic, right there, really requires a good understanding of three-dimensional geometric algebra, regular vanilla, I guess I call it vanilla 3D geometric algebra, which is going to be very easy for us to study because we're just going to be building a different geometric algebra than the spacetime algebra we've been working with, and we're actually making one that is arguably simpler in the sense that it has fewer dimensions in its core vector space. Instead of having gamma 0, gamma 1, gamma 2, and gamma 3 as its, I want to make those commas, as its core vectors, it'll just have E1, E2, and E3, which will be the standard vectors of regular three-dimensional space that we've all learned about. And so we are going to study a simpler geometric algebra, but one that's almost always introduced first. I mean, I've seen a lot of introductions go from 2D geometric algebra to 3D geometric algebra. I actually don't like that. I would rather just start at 3D. I don't like starting at 2D and then adding a dimension. 2D is almost too simple in many ways. And so let us begin with that study, and then once we're really comfortable with it, we will come back and focus on this notion of relative frames and paravectors. So let's begin. So if we're going to create three-dimensional geometric algebra, and I'm going to I say in a hurry, but like I say, we can do this in a hurry because we've already got the basics down. All we're going to do is say that we only have three fundamental vectors, and from those three fundamental vectors, you can create three fundamental bivectors, and you can only make one trivector, and after the trivector is nothing. So now, instead of having the direct sum of 5 different graded vector spaces, we are the direct sum of 1, 2, 3, 4 graded vector spaces. And when we have our three basic vectors, what else does geometric algebra need us to show? Well, in order to satisfy the rule that a vector squared has to equal the magnitude, or a real number, right? Has to equal a real number. In order for that to be the case, we have to supply a metric. And we're talking about regular vanilla three-dimensional geometric algebra. So that metric is going to be this reflected in this dot product, which will be reflected in the notion of the spacetime product as the contraction part of the spacetime product of EI and EJ. It will end up being delta IJ. The contraction part will be delta IJ. The expansion part will always be EI wedge EJ. And if I and j are the same, that could be 0, or it could be EIJ, right? So that's the only difference now is we've reduced the number of vectors and we've changed the metric. Now, our metric in spacetime algebra has a very similar EIEJ, but it goes to -1. Notice that this is a positive 1. We're talking about +1 now. There's no equivalent to an E0 where E0 squared is saying, well, E0 squared is +1, and then EI squared is -1. That's not how this works. The EI squared is +1, and there is no E0 that's distinct by having some other scalar as part of its metric function, as part of the definition of the metric. That doesn't exist here. Now, having said that, I do need to alert you to, if you study this on your own and you go out there looking for other additional information, there is a potential confusion. There is out there in the world 3D geometric algebra, but it's three-dimensional in the sense that it's supposed to work with three-dimensional objects, but it's called projective geometric algebra. And it's still geometric algebra. It's exactly the same sort of architecture we've been describing, but instead of vanilla 3D, it's actually something else. And it does have an E0 here. But so it's really four-dimensional in this sense, right? Because the basic vector space here is four-dimensional. So you do have, you're going to end up with 6 of these, and you're going to end up with trivectors. And this guy is going to be the full-on E0, E1, E2, E3. But in the metric definition, you have E0 squared equals 0. Really interesting, right? And it turns out this is very useful in computer science type applications. It allows you to do rotations and translations in very interesting ways. We're not discussing that. I only call it out to your attention because if you go out there looking for, how do I do three-dimensional geometric algebra, you might end up finding yourself studying this and wondering what the hell this is, which is fine. I mean, it's a really interesting subject. I'm certainly no master of it, but that's not what we're talking about. We are just talking about this, what I'm going to call vanilla 3D geometric algebra. Okay, so once you have established the graded structure, right? We've got the graded structure all written down here. We know the basis for each of the different graded subspaces. We could write down an arbitrary multivector as alpha, a scalar, plus v, which is a vector, plus f, which is a bivector, and beta I, where beta is a real number and I is the pseudoscalar. So this overall thing is a pseudoscalar. Remember, I say I is the pseudoscalar, and then I call beta times I a pseudoscalar. So you still have the potential for a complex scalar, right? A plus beta I is certainly still a complex scalar. And although I've never really seen it, you do have the potential for a complex vector, right? Because v plus wi could be arguably a complex vector, but now wi is the dual of a vector in three-dimensional space. So the dual of a vector in three-dimensional space will be a bivector. So it's not a vector plus trivector, it's now vector plus bivector to give you what might be considered a complex vector. Don't have to worry about that too much. I don't think we run across complex vectors in the 3D geometric algebra, at least in the level that we're going to discuss it. But just as before, an arbitrary vector where I will now put a little arrow over the top. I'm going to go back to this arrow notation. I won't do it for the basis vectors, but I will do it for general vectors as long as I can remember. But a general vector is going to be alpha E1, beta E2, Charlie E3. And you can definitely think of these as unit vectors along the axis in a three-dimensional Cartesian system. Not a problem. And I've written down 2 such vectors, DE1, FE2, and GE3. And now we're going to just start exercising. We're going to go to our familiar, regular Gibbs Heaviside classic vector analysis and kind of try to draw linkages between that and the geometric algebra analyses. So x dot y, right? We know how to do x dot y in normal vector analysis, which for this version of x and this version of y, you'll just get AD plus BF plus CG. And if we did x dot y in our geometric algebra form, we would end up with this collection of 9 terms with these where the dot products are all pushed into the basis vectors. And then we'd realize pretty quickly that the only basis vectors that survive are these diagonal ones. The rest of them all go to 0 by the definition of the metric in three-dimensional space. E3.E1 is going to be 0. So that is, that converting the dot product from the standard vector analysis to geometric analysis is particularly easy. And that's because the dot product is literally defined in standard algebra through this metric, and that's actually borrowed wholesale by the geometric algebra. It just drops right in to the geometric algebra. The cross product takes a little more thought, in standard vector analysis, I always learned to do the cross product if I had to in a pinch by this determinant, right? I'd write down, the vector x components, the vector y components, and then these basis vectors, and then I would calculate all these little minors and keep track of the sign and everything, and then this would be the cross product of two vectors. What's interesting is we can compare this with the wedge product between these two vectors. Oh, that shouldn't be a hat. That should be a little vector symbol. So we could calculate this wedge product. So let's do that. The wedge product of x and y. When you replace x and you replace y with with our definitions of x and y, which were these guys here, right? These two things here. And then you expand by linearity, expand the wedge product by linearity, you basically get these 9 terms, right? And now you have to keep track. Nothing goes to 0, nothing goes away, but you do have to remember that E31, right, is the opposite of E13. So if I wanted to turn everything into E13, I would flip these two and change this to a minus sign. And when you exercise that, you end up with this expression right here. And this looks a lot like the last one we had, right? It looks just like the cross product, where these are determinants of 2 by 2 matrices. And if we lined it up, you'll see that they are basically these matrices, the same ones, right? This is AF minus DB, and here we got AF minus BD, and then we have a minus AG minus CD. Oops, did I say AG? Minus AG minus CD. AG minus CD with a minus sign right there. And here we have BG minus CF. BG minus CF. But notice here, these are vectors, right? This vector cross product yields a vector, right? E3, E1, E2. But our work over here yields a bivector, right? E12, E31, E23. That's not the same thing, right? Here, the wedge product between two vectors is a bivector, as we would expect from geometric algebra. But what we can't run away from, or we can't take our eyes off of, is the fact that the coefficients are the same as the cross product from your standard vector analysis. So to make contact, if we take the dual of this wedge product, right, by throwing an I over here in each case, that dual is, the dual of a bivector is a vector in 3D algebra. The dual of a bivector in spacetime algebra is another bivector, right? Because in spacetime algebra, there is I guess the way to think of it is there's 1, 2, 3, there's 4 rows or 4 different graded subspaces here. But in 4-dimensional geometric algebra, there's 5. And that middle one is its own dual, its self-dual. But in this case, in the 3-dimensional version, there is no self-dual. So in 4-dimensional geometric algebra, bivectors are their own dual. But in 3-dimensional geometric algebra, bivectors are dual to vectors, which is really sweet. Because it allows us to then find the dual of this bivector, which we know will be a vector, and we come up with E12, E123 if you calculate this out by doing the basic things, right? I swap the 2 with the 1 and grab a negative sign, then the 2's square to 1, and the 1's square to 1, which leaves E3 with a minus sign in front. Likewise, you can do it here and here the same way, and you get minus E2 and minus E1. And then when you work all that out, you end up with this expression, which is exactly, it turns out this is exactly these minus signs here, if they were plus signs, it would be exactly right. So what you do is we now say, okay, we're going to take, so the dual of this bivector is exactly the cross product of those two vectors in regular three-dimensional vector analysis, but with an additional factor of -1. So we take a -1 and we put it in front, and I should have an equal sign here. Right? So if we throw a minus sign in front, then it will equal x wedge, vector x wedge vector y I inverse. That's the minus sign is nicer because you can say you take the dual of the wedge product and you take the opposite of the dual of a wedge product. Here you're taking something that's not quite the dual because the dual is with I, but I inverse equals -I for this algebra. And then when you run it through, you've defined this vector cross product. So it's a long way of saying that the vector cross product is equal to minus the vector wedge product, the dual of the vector wedge product, So that is how we define our cross product. So we're making contact between regular three-dimensional vector analysis and our geometric algebra. Now, so what's interesting is imagine we tried to do this in five-dimensional space, because what's really important, I'm trying to, as an example, I use five-dimensional space here. We'll see in a second what I mean, but notice that the cross product of two vectors is another vector, right? Because this is a bivector and the dual of a bivector is a vector, right? And that's just a factor of -1. So imagine that we tried to create a cross product in, say, five-dimensional geometric algebra, where we have scalars, 5 vectors, a whole bunch of bivectors, a whole bunch of trivectors, and 5 pseudo vectors, right? And 1 pseudoscalar. Well, if you take the wedge product of two vectors, you get a bivector. And if you took the dual of a bivector, you would end up with in this five-dimensional case, you would end up with, the dual would be a trivector. So you would have some function of a vector and another vector, and you want it to be a vector, right? For it to be a cross product of two vectors, you're expecting another vector out, but you don't get a vector out. You get a trivector out. You get something really fancy out. And that's why they say there's no equivalent to the cross product in higher dimensions, because because this is the generalization of the cross product, but the generalization doesn't insist that the output be a vector, despite the fact that the inputs are two vectors. And that, for example, in 5 dimensions, you calculate this, you're going to end up with a trivector. But just so happens in 3 dimensions, this turns out to be a vector too, which gives us this nice notion of a cross product. What else is there to say about the cross product? So notice that whenever we learned about how to make the cross product in regular vector analysis, we understood that it only made sense in the context of the right-hand rule. If you didn't know how the right-hand rule worked, you couldn't do this calculation. And over here, notice we haven't discussed anything that looks like a right-hand rule. So what gives? If the definition of this cross product is so dependent on the right-hand rule, well, we take seriously, let me fix this y, and if we take seriously the notion of this equality, right? This equals this. Where's the right-hand rule manifest over here? And the answer to that question is it's manifest in a choice that we made earlier when we chose I to be E1, E2, E3. Had we chosen I to be E2, E1, E3, if that was our definition of I, maybe I'll call it I prime, then we'd be dealing with a left-hand rule. But the right-hand rule is encoded in our definition of I, right? And so we don't have to carry it around ad hoc. It's part of our structure from the beginning, which is, I guess, arguably another little benefit of geometric algebra, is that once you establish your pseudoscalar, then you've basically nailed down this right-hand rule theory, right? In fact, some people say, oh, let's define a geometric algebra. And when they define a geometric algebra, they say, well, that means we have to define I and the metric, right? And that's the entire definition. That's everything you need for the geometric algebra. Because once you define I, you've basically are asserting how many vectors are there, right? So the dimensionality of I is the dimensionality of your space. And by defining I, you've picked up on the order that your pseudoscalar is going to take, which determines the handedness of the geometric algebra. So all that really remains is the metric. Everything else can be constructed from these two things. So I've seen geometric algebras as like, define a geometric algebra, we'll call it G. And G is given by some pseudoscalar and some metric, right? I don't know why I'm using gamma for my metric. I should be using, say, eta. I think I'm more typically using eta, right? Even eta ij or eta ij, right? But buried inside, once you've stated I and the metric, everything else can be reconstructed, or as far as I know. Okay, so that allows us, we've made contact with our vector algebra dot product, our vector algebra cross product. So what else? So the notion of linking vector algebra to geometric algebra is a big topic, and I think I'll find inspiration from this Wikipedia article, which goes through many of these different topics of comparison. And we'll just sort of show how we've learned enough to fully understand all of these topics. And I've just figured, well, if it landed in the Wikipedia article, it's got to be pretty important. So we should go through them. And this will get us sort of up to the fundamental standard of understanding how three-dimensional geometric algebra connects with regular vector algebra. And it's totally worth our time. So let's look at some examples that they use on the Wikipedia page. I like to do this because this is where you will go as a student to learn these things. So going through it and showing you that sometimes the dry language of Wikipedia is no longer that confusing when you kind of focus in on their usage and understand how it links to the things that we've discussed. It actually becomes pretty simple. So let's begin. I pulled out this one. They talk about the equation of a plane. Here they show the regular vector algebra statement for the equation of a plane, and here's the equivalent wedge product equation. And this is pretty fun because we can imagine we have a point R0, a point R1, and some other point R2, right? And now understand these are meant to be vectors that live in the geometric algebra. That means these are all elements of the geometric algebra. You can almost think of there's a little origin of coordinates out here, and this is the vector R0, and this is the vector R2, and this is the vector R1. And when you formulate R2 minus R0, what you're really formulating is this vector here, right? And when you formulate R1 minus R0, you're creating this vector here. And when you formulate the cross product, you're creating some vertical vector here, that is this cross product, is that vector there. And so now, this last part, you take some other point in space, R, right? R could be literally any point in space. The vector R minus R0 is this vector here. That's R minus R0. These are vectors inside the algebra. And the question is, well, if you take the dot product of that vector with this vertical vector, with this cross product vector, that better be 0, because if there's any projection of this vector onto this vector, then this vector certainly does not lie in the plane contained by R0, R2, and R1. So that's the origin of this formula. This cross product dotted into this vector had better equal 0. Now, in geometric algebra, it looks slightly different. We reconstruct the same two difference vectors, right? These two here match those two, but now we create a bivector. We don't create a cross product vector, we create a bivector. So we actually create this little plane element that has its orientation. And now what we say is we're going to look at this other field vector, say the point is out here, r, and we're taking r minus r0, which is this vector here. And now we're going to take the wedge product of that with this bivector. So to be really clear, the idea is this guy here is a bivector, and we're taking the wedge product with a bivector. So the ultimate result is a trivector. But if this guy here only has components that are not linear, if all the components of this vector are linearly dependent on these two vectors, then this trivector, which represents a three-dimensional volume, this trivector, which would look something like this, I suppose, some sort of volume element, will have zero volume. And that is the basis of this equation. Let me see if I can draw this a bit better. Yeah, I guess something like this. It's not that much better, but this is a trivector volume. And obviously, if R is in this bivector plane, which means that this last vector is linearly dependent on these two, then as this gets closer to that plane, this volume shrinks, and eventually it has to be zero, and you have the equation of a plane. So that is how this equation of a plane is handled. What's interesting here to understand is the thing that to keep in mind is actually the obvious stuff, right? The stuff that should be really simple is these vectors are in fact vectors in the 3D geometric algebra, so that R0 is some R01 E1 plus R02 E2 plus R03 E3, and likewise for R1 and for R2. These are vectors in the geometric algebra. And ultimately, these wedge products are all handled between these assumed to be orthogonal unit vectors. Okay, so what next? Well, what's another obvious thing that we do all the time in regular vector analysis? We project and reject vectors. This is a very simple idea, right? We have some arbitrary vector v, and we have some arbitrary unit vector u hat. And our question is what is the projection of v onto u hat, and what is the rejection of v on u hat, which we will designate as parallel and perpendicular. This is not completely unambiguous because it's v parallel to what? Well, we know it's v parallel to this unit vector, which we're going to call u hat. Now, u hat is not necessarily a basis vector, right? U hat does not necessarily equal E1, E2, or E3, right? It's just a unit vector out in space. So we're interested in the projection and rejection onto some unit vector. And this is one of the places where some of the notation gets a little bit annoying, right? U hat can be identified by any vector u. If you divide by its magnitude, it suddenly becomes a unit vector, right? So sometimes you see formulas that are done just in terms of unit vectors, like this one, and then sometimes, no, they give you the regular vector and they normalize it. And so these normalization coefficients come out and kind of clutter up. They kind of stink up the joint, right? Instead of just having, u hat here and u hat here and u hat there, you always get these normalization coefficients. But don't let that fool you. Once you kind of realize they're just normalizing everything, your brain will automatically convert these kind of equations to those kind of equations. So the first thing we take note of is that the projection onto u hat of v, oh look, see they have a typographical problem here. They're trying to put u hat in the subscript of the word projection, and they end up with this huge gap between the hat and u. Just bad use of LaTeX, I guess. But regardless, they want to show that okay, the projection of v onto u hat is simply given by this expression. And this is a geometric algebra expression, right? It's the space-time product of the unit vector u with the dot product of u hat on v. And in geometric algebra, this dot product is simply the metric product. Sorry, not the metric contraction of u hat onto v. So this is actually true in both regular vector algebra and geometric algebra, because this is a number. Remember, when you have two vectors and you take that dot product in geometric algebra, and it's the same as in vector algebra. So this is a number times a unit vector. And so we know the direction is in the right direction because the projection is in the direction of u. So this is a place where the two are literally the same. The two, meaning geometric algebra and vector algebra, are literally the same right here. And the way you need to be able to see this now is when you see this, you always know you're dealing with a real number. And the space-time product of u with a real number is simply real number multiplication. It's a scalar, it's like a scalar vector. It's a scalar product between a scalar and a vector. So then they make the obvious point that orthogonal to the projection is the rejection, right? So here's the projection, here's the rejection. So if you take the regular vector and you subtract off its projective part, this is equal to the rejective part, right? And here they have all these unit vectors set up. So this is purely, this formula is literally this formula. The two u squares cancel, giving you v, right? So these two u squares cancel, and so this v is that v, and these unit vectors here are simply this divided by the magnitude of u, and then this guy divided by the magnitude of u, which is, when you combine those two, you get this u squared product, and that's these two guys. So this is a literal translation, just with the only distinction here that they're just saying projection and rejection onto a vector u, right? And you have to normalize it. So now what they're going to show is that the rejection can be expressed as a single geometric algebraic product in a few different ways. So this is kind of important to see. Let's look at this. Start with the obvious statement that a vector is the magnitude of a unit vector times itself. The magnitude of a unit vector is 1. But we know from our geometric algebra that this magnitude is given by the space-time product of a unit vector with itself. So we can immediately substitute u hat for the magnitude of u squared, as long as it's a unit vector like that. If it's not a unit vector, then this isn't true. But it is a unit vector. So now we just execute the space-time product of u hat and v, because remember, it is associative, right? But we know from our definitions of the space-time product of two vectors, that's u dot v plus u hat wedge v. So now we are all the way over here. So now we have u dot v u, right, which is the projection part, which means this is what's left over. So this must be the rejection, right? Because if this is the projection, it's the projection plus the rejection, which equals the vector itself. So I can still write down v, the whole vector over here. So this becomes v projection, and this must be v rejection. So right away, we know that v rejection is u hat wedge v. So that is our answer. But notice, this better be a vector. Well, we know how the space-time product works between a vector and a bivector. We've kind of memorized that, right? And that, and by the way, I've noted that you can do this from the other side too, right? So this also equals the rejection. Notice the bivector is reversed and the space-time product comes on the right-hand side. But one of the things anybody at this point should be able to do is write down this product, which is u hat dot u hat times v minus u hat times v times u, right? But this guy here is just equal to 1, right? That's 1. So this equals v minus u hat dot v u. But this is v parallel. So clearly what's left over is v rejection. And indeed, it's a vector, right? Indeed, this is a vector. So that's your basics of projection and rejection. This is the formula for rejection. Projection is really easy to see. It's this rejection one that you have to kind of work through a little bit, but not very hard. Well, and by the way, if we go through the rest of the projection, rejection on Wikipedia, we see that they compare the vector algebra form here with the geometric algebra form here, right? So the vector algebra form has this triple cross product where the unit vector appears twice. And then they also try to show just a few other things. This again is the form when you don't have unit vectors and you use you're using this division notation, which I don't like. I rather write u inverse as opposed to 1 over u. But u has an inverse, so it's nice. Here's a nice one that's a good exercise to work through. What is the area of a parallelogram defined by two vectors u and v? And what they do is they show you how you would do it in regular vector algebra. You take the cross product of u and v and find its magnitude squared, right? This is a vector, and this is the magnitude squared of a vector. But this is in geometric algebra, this is opposite the value of the bivector squared. And that's really interesting, right? Area's got to be positive. So this bivector squared obviously is negative because you're taking the opposite of it to get a positive number. So flushing this out is actually totally worth doing. So let's take a moment and flush out why this is the case. Remember, we're expecting this to be a number because this is a number. Area squared is a number. Okay, so the setup for this is a vector u and a vector v. They obviously form a plane. And I want to find the area of this parallelogram. That's this little piece of plane that those two vectors define. And that area is clearly the magnitude of u times the rejection of v on u. So this guy right here is v rejection. And so I need the magnitude of u times the magnitude of v rejection. Well, the magnitude of u we can just calculate from knowing u. We now know how to calculate v rejection two ways. We can calculate it as the geometric product of u times the bivector of u wedge v, or the geometric product of the bivector v wedge u with u, right? We have those two options. Just remember, depending on how we derive this from either using u hat v, or v u hat in our previous derivation on rejection. So with that in mind, let's just push the calculation forward using this one for now. And I get rid of this u hat. Well, I get rid of this u magnitude by replacing u hat with u and dropping this magnitude in the bottom. I explicitly normalize. I'm taking this and I'm explicitly normalizing it. Regular u, the vector u, which I guess now if I do that, I probably should put a little arrow up on top there, right? And once I do that, I drag down a magnitude of u, which will cancel, right? So I end up with this area equals the magnitude of u hat, geometric product with u wedge v. Or if I'd followed this track, I would have ended up with the geometric product of v wedge u against u hat. So I have this nice expression for the area. Squaring the area is just multiplying these two things with each other. Now, first of all, these are numbers, right? Because I have a vector geometric product with a bivector, right? And that geometric product, we know that when you take a vector, geometric product with a bivector, you end up with a vector. We've done that multiple times. In fact, I can do this in my head now. It's u dot u times the vector v minus u dot v times the vector u, right? And that ends up being the u dot uv is v, and so it's v minus its projection, right? So that's what this is. This is v minus its projection. And so this is a vector inside here, and the magnitude of a vector is a number, right? That would be the vector dotted with itself, square root of that. So I'm going to get rid of these magnitude signs by just squaring everything, right? So I end up with this vector squared, which by the definition of the geometric algebra is a number, because this is a vector, so squaring it gives us a number. So I can square it by taking this and multiplying by this way, or I could take this and I can take this one on the right-hand side and multiply it by the one on the left, which is actually the preferable way of doing it. This doesn't get you very far, but doing it the other way puts these two u's next to each other. Space-time product of u hat with u hat is 1. So I'm left with this bivector, space-time product with this bivector, and I just flip these two around to get to introduce a minus sign, and then I have the bivector squared. The bivector squared. I'm being a little careless here with my hats, right? These hats here need to be actually vectors, right? So all of these hats on these u's that are inside the bivectors actually need to be vectors, right? Okay, so I put back these vectors. This is the full vector u here that we're dealing with, right? And this guy will ultimately be a number. So when I say this guy must ultimately be a number, you have to be confident in this geometric algebra with this kind of stuff. And it takes a while. I mean, I'm still struggling with it now. When I look at that, I'm like, well, how do I know that this guy is a number? And this is a good time to let's go calculate it, right? Let's calculate the geometric algebraic square, the geometric product square of a bivector, which is a bivector's geometric product with itself. And let's just hammer through it, do it the hardest possible way, right? We'll speculate that u is some vector, AE1, BE2, CE3. We're going to do it with basis vectors. And V is DE1, FE2, GE3. This is the hardest way you could imagine doing it, because we're actually casting it in a basis to see that everything's going to cancel just right. Because in principle, remember, a bivector could have a quadravector part, a bivector part, or a bivector product could have a quadravector part, a bivector part, and a scalar part. Now, there's not going to be any quad vector part, because in three-dimensional geometric algebra we know there's no quad vectors. But why doesn't it have a bivector part, for example? And normally a regular bivector product would, but the fact that it's a product with itself is what's so special, right? So if I just take this wedge product between u and v, I just take the wedge, the vector u there, vector v there, and I wedge them together, right? And if you do that, you end up with this determinant expression that we'd actually studied earlier, right? We actually studied that this wedge product is going to be a bivector, right? This is a bivector, and here are the bivector basis vectors. And the coefficients are just going to be little 2x2 determinants of the various coefficients from the definition of the two vectors. And that exact formula exists on Wikipedia, right? And where they compare the same formula for the cross product with the bivector product. Now notice, right, this cross product is a vector, because EI cross EJ is a vector. And but here, this is a bivector. So in order to make the equate the two, I need to multiply this guy by I and take the negative, right? And then these two would actually be the same, because when I take the dual of this bivector, I end up with a vector, right? And that's what this is. But that aside, so once I have that product down and I realize that these factors, of course, they're real numbers, I'm going to take this object, which is the object we're trying to square, and I'm going to literally write it as a space-time. I keep saying space-time product, but I mean geometric product now, because we're not doing the space-time algebra. We're doing the regular three-dimensional algebra. For example, when I mentioned I a moment ago, I is actually E1, E2, E3, right? There's no E0 in there. So now I just lay this thing out, and what I've learned is, okay, these are real numbers. And so what I'm going to do is I'm going to take these real number coefficients, and I'm just going to replace them with letters so I don't have to write so much stuff each time. So I replace, this determinant with A12 because it's the coefficient of the bivector E12, and A13 is the coefficient of the bivector E13. Pretty simple idea. And then I just execute this geometric product, which distributes over addition, and I end up with all of these terms here, right? And what I mean by these terms is I basically just FOILed out this product up here, and I end up with products of the coefficients and geometric products of the bivector basis vectors. And so I'm expecting that, well, look, this has got to be a real number, so I'm expecting somehow some of these are real numbers, some of these are bivectors. The bivectors better somehow go away. And of course, by now I know that, there's going to be cancellations due to sign flips and things like that. But I really have to dig into each one of these. Oops, this probably should be, to be a little more clear, should be E13 like that. So I have to dig into each of these geometric products of these bivectors and see how they resolve. And if I just start at the beginning, I know that E12 is actually E1, E2, E1, E2, so it's simple notation. But that equals the opposite of E1, E1, E2, E2, because these are orthogonal, so I can anti-commute orthogonal vectors in a geometric product, right? There are little facts like that you just got to remember, or none of this makes sense. It kind of gets... And when I say you've got to remember them, I guess what I mean is if you're going to be using basis vectors a lot, you have to understand how to handle and manipulate basis vectors, and you want them to be orthogonal, and you can commute orthogonal basis vectors, right? I guess in some sense you could say, okay, I remember the geometric product of EI and EJ is defined by EI dot EJ plus EI wedge EJ, and they're orthogonal, so this goes away, that's what's left, and that's an antisymmetric object. So I guess, keeping these running through these fundamental notions over and over again until you're really comfortable with them is totally fine. I'm doing it right now, right? I'm trying to square a bivector, right? It's awfully late to be struggling with that, but it doesn't hurt to go through it again. So anyway, this ends up being minus E1 squared, E2 squared, and remember the fundamental principle is that these guys are simply numbers by definition in our geometric algebra, and because the metric is Euclidean, this equals minus 1 times 1, which is minus 1. And this is an important point, by the way. Bivectors, see, this is E1, E2 squared, right? That's what this is. This is E1, E2 squared. The square of bivectors is minus 1. And that's an important principle that we're going to discover for when we study rotations. But anyway, the point is if you can pair up all the indices, right? If you can pair up all these indices, then you are going to end up with you're going to end up with a real number, right? And if you pair them with one flip, then you end up with that real number is going to be -1, right? If you have so here we need one flip to get the 2's and the 3's together. Here we need one flip to get the 1 and the 3's together. Here we need one flip to get the 1 and the 2's together. So these sort of diagonal terms, I guess we could call them that, all end up being -1. So that means obviously this process doesn't work as well for, say, E1, 2, E2, 3, which is E1, E2, E2, E3, which is equal to, now we don't need a flip at all, but is equal to E1, E3, because this guy goes to 1, right? That's E2 squared, it goes to 1. E1, E3 is E1, 3. So E1, 3, this is replaced by, this guy here is replaced by E1, 3. But it's not too hard to see that you're going to do the same game down here, but you're going to take 2 flips to get the 2's next to each other. So the -1 goes away, and you're going to end up with E31, right? And in order to match the E31 with the E13, you have to do one more flip. So you pick up a minus sign, right? You pick up a minus sign, but the coefficients are the same, right? So these coefficients will actually match, but this guy will be minus E13. So that is going to cancel with that, and that process is going to happen for all of the off-diagonal elements. And so the only thing that will survive are the diagonal elements, which are real numbers, which is exactly what we said. Now, this wouldn't have been true if we weren't squaring a bivector. If we just take 2 arbitrary bivectors, A and B, and multiply them together, what you can clearly see is you're going to get these real number parts, but these things won't cancel. This guy here will not cancel that guy there. You'll have a leftover E13 bivector, and that's the bivector part. And the way we expressed this before was something like this. We said the geometric product of 2 bivectors was A dot B, A cross B, and A wedge B, right? And in 3-dimensional algebra, A wedge B is always going to have 4 parts to it. So that's going to be, that's not going to exist in 3-dimensional algebra. A cross B, we remember we had defined by, we used this same little cross product, but here what we're talking about is A, B minus B, A over 2, right? But when A and B are the same, that's just A minus A. Well, so that part goes away, and we're left with just this A dot B part. So, but this is sort of a formula you have to remember. Oh, bivector multiplication is this process. Bivector trivector multiplication is some other process. So in principle, you can always do this. You can always blow up whatever 2 objects you're trying to multiply into its component forms. Even if it's some weird multivector that has trivector and vector parts, you could ultimately do this process and break down everything into its vector component parts. Look at the ones that are 0, look at the ones that are scalars, look at the ones that are vectors, trivectors, and kind of work backwards that way. Anyway, the point is we've now shown that this guy is in fact a real number, and we've also shown that it's negative, right? Because we have these negative ones. These guys are squared. The coefficients are all squared, so they're positive. So we know that this sum is negative. So to get our positive area, we have to end up with it. That's what explains this minus sign in front of this square, because that square is always going to be a negative number. So that explains that minus sign. Anyway, so that exercise for this parallelogram or this parallelogram area, it's a good exercise, especially if you really make sure you understand all the parts and go through it all like we just did. So the next one's fun. It's the angle between 2 vectors. And in geometric algebra, such an angle is just as logical as anywhere else, because we're dealing now with this vector space. So a vector u and a vector v, there will be an angle between them. And obviously the sign of this angle, which seems to be the way they are doing it here in Wikipedia, is going to be the vector rejection of v on u with the size of V itself. So you could actually write this as this, the size of the vector rejection divided by the magnitude of V. And this is the vector rejection against U, right? Ultimately, I guess what we're dealing with is this would be here, this would be the vector rejection, and this is our 90-degree angle, and we're interested in the sine of theta. So we know that this vector rejection is U hat, not U hat, just U, right? U wedge V, and then and underneath that we just want the magnitude of V. So the way we're going to do this is we will square the top, because we also know that the rejection is also given by. So we're going to calculate this quantity squared, which is this thing squared, which is this thing squared, which is going to be V wedge U hat, U wedge V divided by V squared, where V is just the vector. And then we use our same principles as before. These two guys multiply, to +1, but we have to flip these two to get the square, so we get minus U wedge V squared, which we now know is a real number, over V squared, and that equals this sine squared here. So that's where this expression comes from. So now we've actually kind of beat to death how to calculate this numerator. So, and the denominator, of course, is just the metric contraction of V with itself. And the next thing that I found on the Wikipedia that they felt is an important thing to understand is the product of a vector and a bivector, understanding how that works. Now, we've discussed this a bunch, and it all kind of comes down to these four equations here. So we'll just cut to the chase on this. You know, the product of a vector with any multivector, if we remember, it's always going to be a contraction and an inflation, right? The contraction part of the multivector will always, so say it's a blade R. The contraction part will always be omega AR, the geometric product of the vector omega with any blade of any degree R will always have an R minus 1 piece, and it will always have an R plus 1 piece. Unless, of course, R plus 1 is greater than the dimensionality of the space, in which case that part won't be there. So the thing to remember here is, okay, this dot product is always, when you have a vector involved, this dot product is always going to represent the contraction part, and the wedge product will always represent the inflation part. And when we did this a moment ago with in our calculation of the area of a parallelogram, you may remember right here we had a vector times a bivector. And when we did this, I wrote down this vector times a bivector. I wrote it down as only the contraction part, right? Because a bivector is, the R in that case is 2. So the contraction part is going to be an R equals 1, or a grade 1 element, which is a vector, and that's what this is. But I didn't write the inflation part down because we know that U wedge V is 0, because U wedge U is automatically 0. And that's what we need to remember from the stuff that we're getting from this collection, right? This part sometimes is 0 when you do this. So we immediately went from here to here. Now notice you have this dot product, right? The dot product is very specifically defined in this expression for a vector and dotted into a bivector. This is one of those derived products that we're really using to say the contraction part for the vector. And this is one of the issues in geometric algebra that I've discovered, is that there's this proliferation of dot products out there. There are many different dot products. And the Wikipedia page actually addresses this, but we're not going to get down that rabbit hole yet. It's a rabbit hole that I do want to address later, but we're not going to address it right now. So ultimately, this is our survey of three-dimensional geometric algebra in some of the basic form. But the big bugaboo that we have to attack is rotations, reflections. And that we're going to do in our next lesson. And that's really critical. And three-dimensional geometric algebra is definitely the best place to be introduced to the notion of rotations. And then when we apply it to our spacetime algebra, we'll see how it takes care of all Lorentz transformations, which is really exciting. So I'll see you next time.